So this is the start of the exam papers for organic. These are normally question 8, but in 2018 it came up in question 10. Let's have a quick look at this. The first question, would you expect benzene to readily undergo an addition reaction with bromine water, and explain your reasoning? And the answer for that one is actually very simple, and the answer is no. So one of the main reasons why is because benzene is stable. Benzene's a very stable molecule. And that's all that's required there for that, nothing else. But it's the next one that I wanted to get a look at. Some of the electrons in the benzene molecule are delocalized, and it asks you to explain the underlying term. So it's a very quick explanation, but let's try and figure out what does it mean when it says it's delocalized. So for example, let's have a look at what the benzene molecule actually is. So when we draw benzene like this, it's similar to cyclohexane. It's got the carbons all the way around. And what happens in here is you have generally a double bond, single bond, double bond, single bond, double bond, single bond. And that's our standard benzene, and that's how we draw it. Now, if we draw that out to show you what it looks like, the expanded structure is like this. And then we have double bond, single bond, double bond, single bond, double bond. So you have to understand what each one of these mean. So let's take a color here. I'll take the blue one. So each carbon has got to have 4 bonds around it, tetrahedral. So what we have is a carbon with a hydrogen off the top here, and a carbon off the hydrogen, and a carbon off the hydrogen, and that's the same all the way around. Each one of these carbons is sharing 4 electrons. So the double bond, so let's say here we have an electron there, we have an electron there, we have an electron here, and we have an electron here. And that's the same for every carbon all the way around the bond. 4 electrons. Carbon only has room for 4 electrons because, again, carbon has got 2 electrons in the first shell, and it's got 1, 2, 3, 4 electrons. So there is only space for 4 electrons. Carbon can't hold 5 electrons. So because of that, this carbon can't get an extra electron. But what actually happens is, and I'll move down to this bottom carbon, let's say we have a look at this electron here on this carbon. This electron moves from this carbon over here to this carbon. The problem we've got there is now suddenly this carbon here has got 5 electrons. So what does it do? Well, it then moves one of its own electrons from here onto the next carbon. And that carbon then has a problem because that now has 5 electrons. It's got the double bond, and it's got the single bond for the hydrogen, and it's got the single bond at the top going up to carbon. So now carbon suddenly has 5 electrons. So it takes one of its electrons and pushes it on again. So that electron gets pushed on here. And then that one has 5 electrons, and then that gets pushed on, and that has 5 electrons, and that gets pushed on. So what ends up happening is the electrons keep getting pushed around the benzene molecule. Because of that, often benzene then is drawn like this, where you will see dotted lines running all the way around. These dotted lines means there's constant movement of the electrons. One electron doesn't just exist to one carbon. So for example, in this example here, the green electron that carbon has here is passed on to multiple carbons. So the green electron starts here, then it ends up here, and then it passes on again, and they keep going around. This is why when we draw benzene, we draw this benzene structure like this. And this is what the circle means. The circle means that there's electrons constantly moving around. This here is called delocalization. In other words, the electron is not localized. The electron is not in the one place. It's delocalized. It's moving around various places. That's why this diagram here is a better diagram for the structure of benzene than the one on the left-hand side. So that's a brief explanation of what delocalization is. Now, what sort of an answer are you expected to give? So looking quickly back at the question again, it just says some of the electrons in a benzene molecule are delocalized and explain the underlying term. So when something is delocalized, you can say that as an answer, the electrons are shared between more than two carbons. Because again, normally with a single bond, your electrons are shared between two carbons only, but in this benzene ring it's shared between more. So this here is your answer, and again, it's a short and sweet answer, but if you don't understand what delocalization is, it makes it very difficult. So hopefully that clears up that. It's a common question that students have. The next part, how many electrons in a benzene molecule are delocalized, and how many involve sigma bonds between carbon atoms? So how many are delocalized? So let's have a look at that question. So again, in this one, if you're actually looking at it, you can see you have 6 carbons. So in this particular example, you have 1, 2, 3, 4, 5, 6. So in this example, because there's 6 carbons and that's where the electrons are and it's moving between those carbons, you have 6 delocalized electrons. The next part then says how many electrons are involved in sigma bonds between the carbon atoms. So how many involved in sigma bonds? So to answer this one, you've got to know where sigma bonds are. So first of all, when you have a double bond, one of the bonds will be a sigma bond and the other one will be a pi bond. When you have a single bond, that is a sigma bond. So if we go back and we have a look at our structure, just for argument's sake, we're drawing double single, double single, double single, and then we have the hydrogens coming off. If you count up, so let's start with the first double bond. So there is a sigma bond here, there's a sigma bond here and a single bond, there's a sigma bond here, sigma bond here, here, and here. So we're at 6 already. And then each of these nodes is a carbon, and each one here is a hydrogen. So that's another single bond. So you've got 1, 2, 3, 4, 5, 6 single bonds there. So that's 6 sigma bonds. So that gives you a total of 12. So when the question is asking exactly how many are involved, so how many electrons are involved in sigma bonds between the carbon atoms, then the answer is 12. Moving on to the next part, question 8, and this is 2018. So let's have a look at A part 1. So draw structures to show all the bonds of molecule B and C. So we got propane 1-ol. So we're drawing propane. So we're going to draw 3 carbons. And it's 1-ol. So 1-ol, you have to put the OH group then on the first carbon. And you surround them by hydrogens, don't leave that out. And you should put in hydrogens. You won't lose marks if you leave out the hydrogens, but it's good practice. That's B. C then is propanal. So again, 3 carbons. And it's an al, so it's an aldehyde, so C double bond OH. And again, surround by hydrogens, just making sure there's only 4 bonds between them. Which one of the 4 compounds contains only one tetrahedrally bonded carbon atom in its molecule? And the answer to that is ethanoic acid. So let's have a quick look at ethanoic acid just to see why. So C double bond O, OH. And then what we have here in this carbon is, if you want to see it tetrahedrally, you would have HC and you would have basically a wedge shape with the H coming out here, and you have it going back. And what gives it this shape is this double bond here. So we end up with a bond angle of 109.5 degrees. and that's on those two. Whereas the other bonds have got different angles. So this is the tetrahedral carbon, this particular one here. Okay, move past A onto B, excuse me. Propan-2-ol and B are structural isomers, and B is a primary alcohol. Explain the underlying terms. So your structural isomer, so the first one, so structural isomer is compounds that have the same molecular formula but different structures, or different structural formula you could use there either, which is normally what I use. And then the other one then is a primary alcohol. So a primary alcohol, as we've seen already in the notes, if you watch the previous video, is where the carbon bonded to the OH is bonded to only one other carbon. Now, off on the side, an example of that would be ethanol. So the carbon that's bonded to the hydroxide, the OH, is bonded to only one other carbon, and that makes it a primary alcohol. Then it says part 2, C and another compound E are structural isomers, and then draw the structure for E. So let's have a look at C. C and another compound. So C was our propanol. So if we were to draw out our propanol, that's what we have. And it says another compound, that's C. Another compound, E, is a structural isomer. So we've got to try and figure out how to work out a structural isomer. Well, one of the ways you can do it, you have to keep the same number of atoms, but you have to change the structure. And one of the ways you can do this is maybe by moving the double bond O. So if we kept the same amount of carbons and we just moved the double bond to the middle and then surrounded by hydrogens, and then just check that we have the same amount of hydrogens, and we do. Sorry, I'm missing a hydrogen on that one there. So that's an example that we could use for E. So I don't think it asks for a name of it. It just asks for a draw structure for E. Oh, and part 3, give the IUPAC name then for that. So this one here is 3 carbons. So it's prop. And it's a C double bond O. So that means this is a ketone. So it's propanone, but you have to say where the double bond is. And it's on the second carbon. So this is propan 2-one. Now, technically speaking, you can also call this propanone because there is no other way of writing propanone. For example, if you took this C double bond O and you put it back at the end, it would cease to become a ketone and it would be an aldehyde. So just basic propanone would also suffice here. Part C of that question, think of it as space. So part 1, explain why the boiling point of propanal is much higher than that of butane. So we'll have a go at that first. So see part 1. So boiling point of propanal. So propanal, of course, is an aldehyde. And that's a C double bond O and H. And then butane is an alkane. And the alkane's main functional groups is its C single bond C. So as we discussed in the previous video, this here is a polar molecule. And the reason why it's a polar molecule is because of the C double bond O, the carbonyl group. And it's the carbonyl group that makes it polar. And because it's polar, it forms dipole-dipole bonds, dipole-dipole, with other aldehydes or other propanals. And this dipole-dipole is a strong bond to break. So because of that, you would need more energy, therefore giving you a higher boiling point. Okay, we'll continue this in the next video. We've run out of time.